Welcome back. This is video lecture 30.3, and we're going to be discussing sections 4, 5, and 6 in chapter 30, where we talk about a new kind of circuit element called an inductor, and the circuit property that it has called inductance. I will tell you right here up front that this new circuit element, inductor, and its property, inductance, is the magnetic analog of another circuit element we've already studied a lot, a capacitor, with its property, capacitance. Okay? And so in a capacitor, we separated positive and negative electric charge on two separated conductors, and we created an electric field in the region between those conductors. And we talked about the capacitance of the capacitor as a measure of its ability to separate charge for a given potential difference between its two conductors. Now we're going to talk about the magnetic analog of that kind of situation. And we're going to talk about an inductor as a kind of circuit element. Okay? So what is such a circuit element, an inductor? Well, it's really quite basic. It's any number of windings of conducting wire. Any number of windings looping around of conducting wire. It could be one single loop of wire, once around. It could be what we call a coil, which is really just multiple windings around. It could be a more specific kind of situation, a solenoid, which is when you take a cylindrical frame that's quite a bit longer than its diameter, and you just wrap the wire carefully, turn by turn, from one end to the other. Or it could be a toroid, where you take a solenoid and you wrap it around and connect the two ends together to make a donut shape. So it's any number of windings of conducting wire. And then we're going to pass through those windings electric current. Okay, that's it. That's all you have to have some inductance. Any number of windings of electric wire, and you pass current through it. And as I said, it's the magnetic analog of a capacitor. A capacitor stores energy in the electric field created by the charge separation. An inductor stores energy in the magnetic field created by the current flowing. Because of that magnetic field, you can talk about an inductor creating magnetic flux through its windings. And Faraday's law, if the current in the windings, and therefore the magnetic field from that current, and therefore the magnetic flux through the windings changes with time, we'll have an induced EMF across the two ends of the inductor. That's Faraday's law. Okay, so that's basically what an inductor is and does. Now, an important property of an inductor is called its inductance. That's the property. Just like there's a capacitor, that's the thing, and its property is capacitance. Now we have an inductor, that's the thing, and its property is inductance. And what is inductance? It's a measure of an inductor's ability to create magnetic flux for a given amount of current. So this drawing below shows a simple representation of an inductor. We've got wire there, conducting wire, that we have wrapped around n times, in n loops. Okay? You might want to call that a coil, capital N windings. And we're going to pass current, starting over here on the left, going upward, current I. So it's going up in the front, away from us, into the screen at the top, down at the back, and then at the bottom it's coming out of the screen towards us. So if I imagine wrapping my fingers of my right hand around the coil, the inductor, in the way the current's going, and look which way my thumb of my right hand points, that tells me the way the magnetic field points. And so you see the magnetic field lines that are drawn here. And in general, they are coming out at that end going in the magnetic field lines at that end. So the left end acts kind of like a north pole of a bar magnet, and the right end, in this case, acts like a south pole. So we definitely have magnetic flux through the windings here. Okay? Let's say the magnetic flux through each winding is an amount phi sub b. So the total magnetic flux through the whole inductor is capital N times phi sub b, because I am assuming I have a uniform magnetic field and I've got the same amount of flux through each winding. Now we're ready to define the inductance of the inductor. Okay? The symbol for this property, inductance, capital L. It's defined to be the total magnetic flux that I get, N times phi sub b, divided by the current I put in. Total flux per unit current. Compare that in the electric analog with the capacitor and its capacitance, C. Definition of C is that, Q over V. You can think of that as the amount of charge separation I get divided by the potential difference that I have between the two conductors. Here in the inductance case, it's the amount of magnetic flux that I get divided by the current that I put in. What is the SI unit of this new quantity, inductance? Well, it's the unit of magnetic flux, the Weber. Reminder, Weber is equivalent to a Tesla times a meter squared, divided by the unit of current, ampere. Weber per ampere, or Tesla meter squared per ampere. And just so you know, in the SI system, that combination of units is given its own name. It's called the Henry. That's the unit of inductance, 1 Weber per ampere. Okay, again, in analogy to capacitance, inductance is a geometrical quantity. Depends on geometry, size and shape kind of things. It does not depend on the current I that I'm sending through the inductor, even though I shows up in the definition of L. Okay? Just like capacitance doesn't depend on Q or V, it depends on the shape of the capacitor, even though that formula for C has a Q and a V in it. Well, the analog here is the magnetic case. Inductance is a geometrical quantity. Depends on size and shape of the inductor. Let's take the kind of simplest scenario of inductor, a solenoid that's wrapped around a cylinder of length L and cross-sectional area A. Let me draw one down here on its side. Okay, that's a cylindrical frame that has length A, length L, cross-sectional area A. And then we're going to wrap windings of wire around. Okay? I'll draw a few of them like that. But they go, and first of all, they're going to be really closely spaced, and they run the whole length. And through each winding, I send some amount of current around I. Okay? Right, that's a solenoid. It's got length L, cross-sectional area A. It's also got little n turns per unit length of the wire. What's the inductance for such an inductor? I'm just going to state the result first, and then I'll show it. It's got mu 0. That's the magnetic permeability constant that shows up everywhere in magnetism, just like epsilon 0 shows up everywhere in electrostatics, including in capacitance, times little n squared, the number of turns per unit length squared, cross-sectional area A times L. Doesn't depend on the current I, just depends on geometry. Okay? All right, let me show you where that result for the inductance of a solenoid comes from. So I've got that sketch of a solenoid. I've got the windings of wire going around. See how the current's going? Down in the front. So let me sketch the way the magnetic field points inside there. Going to have a nice uniform magnetic field inside the solenoid. Wrap the fingers of my right hand around the cylinder the way the current in the wire is going, and look which way my thumb points. It points to my right. So in the interior region here, I'll have a nice uniform magnetic field B to the right. and pretty much no magnetic field outside. So I can ask, what's the magnetic flux through one winding? That's what your book would call phi sub b. And since I have a nice uniform magnetic field, the result will just be the magnitude of the field times the cross-sectional area. And the magnitude of the magnetic field for a solenoid is mu0, number of turns per unit length, little n, times the current in each turn. So that expression right there is the magnetic flux through one winding. So for n windings, what is the expression for the total magnetic flux? Well, I'll just come down here. That would be N times phi sub b, right? So that would be N, big N, mu0, little n, I, A, right? There's a big N and a little n. That's a little bit confusing, or potentially confusing. Let's be clear what those mean. Capital N is just the total number of windings. Little n is the number of windings per unit length. We were told what little n was. Yes, remember? We were told that it has little n turns per unit length, so we can't have big N in our answer. But I can express big N in terms of little n. Yes? The total number of windings, big N, is the number of turns or windings per unit length, little n, times the length, L. So let me write that. So I have that expression. And so then I multiply this out a little bit. I get a mu0, little n squared, L, A, I. That's the total magnetic flux. And so now the self-inductance, or the inductance of the solenoid inductor, is by definition the total magnetic flux through the windings divided by the current we sent in. So I just take this expression right here for the total magnetic flux, and I divide it by the current, I. That means the I goes away, and I just have mu0 and things that depend on size or shape. Little n squared times L times A. So if we do have a solenoid for our inductor, and we want to know how much inductance in henries that solenoid has, I would plug in the numbers for mu0, little n, length L, and cross-sectional area in A. Cross-sectional area A in meters squared. Okay? All right. Now, what does an inductor with inductance do when you put it in a circuit? That's what we really want to know, because there's definitely going to be inductance in a circuit. What happens to the behavior of the circuit when you have an inductor in it? Okay, so I want to now talk about what's called self-inductance, and an intro to also what's called an RL circuit. An RL circuit is a circuit that has an R, a resistor, and an L, an inductor. So down here we have a couple of circuit diagrams. Let's first look on the left. It's similar to the circuit diagram we discussed when we learned how to study a charging capacitor in a circuit, RC circuits. In fact, it's exactly the same circuit, except over here on the right, before we had a capacitor with capacitance C. We've now replaced that with an inductor with inductance L. And notice the way we draw a circuit element called an inductor in a circuit diagram. Careful, it looks maybe like a resistor symbol, but it's not. You see how it's got little loops in it? Well, that's because an inductor is loops of wire. So be careful about the way we draw that. That's an inductor with inductance L. So my circuit consists of a source of EMF, curly E, mechanical switch that can be thrown to A or B, a resistor with resistance R, and an inductor with its self-inductance L. And all we're going to do is, at time 0, throw the switch S up to point A, giving me this circuit on the right. One loop with the EMF, the resistor, and the inductor. Okay, now, in the past, the way we would have thought of this is, if it had been a circuit loop with no inductance, that when the minute I threw the switch to A, the current in the loop provided by the EMF is instantaneously at its final value. Instantaneously. But that's not exactly what happens. And with the inductor here, we need to talk about that. Because really what happens when you throw that switch to point A, right at the instant you make contact with point A, the current in the loop is zero. There was no current, right? And I just now made contact with A. So right at that instant, the current is zero. So what has to happen is that the current has to go through a process of change. It has to build up from zero. And so what I have flowing clockwise here, because of the polarity of the EMF, is I have a current I that starts with zero and is going to be increasing with time up to some final value. It's not going to instantaneously change from zero to its final value. It's got to ramp its way up. And so what I have as far as this inductor over here is concerned is I have a current I going downward through it this way by means of the windings, going around and around and around, but effectively going downward. And that the current I is an increasing function of time, which means I have a increasing magnetic flux, which means I have an induced EMF across the inductor. And the induced EMF wants to oppose the change. Faraday's law / Lenz's law. So that induced EMF, which we're now going to label curly E sub L, because it comes from an inductor, notice its polarity. See it right there? See the arrow pointing up? That's the polarity of the induced EMF, because it's opposing the increasing current, which has the net effect of traveling down. So it's important to realize then that in addition to the traditional source of EMF from the battery there, I've got an induced EMF across the inductor, which is upward since the current is downward and increasing. So now we're going to combine Faraday's law. Curly E induced is negative d by dt of n times phi b, the total magnetic flux, along with the definition of self-inductance. That's what the L is called, self-inductance. L equals n phi sub b over I. So that just means that n times phi sub b is equal to L times I, and L is a constant, so I can bring that out front of the time derivative, and I get an alternative way to express the induced EMF across an inductor. Curly E sub L is negative L di dt. So the induced EMF across an inductor is minus L, the self-inductance of the inductor, times the rate of change of its current. Okay, and if I have the current I going downward through the coil and increasing, then the induced EMF, curly E sub L, is upward to oppose that increasing current. It's trying to keep the current from changing, the induced EMF. Now, what if I had the other scenario? Namely, after the switch S had been thrown up to point A and kept there for a nice long time, I just threw the switch from A to B. That effectively takes the battery out of the circuit. Well, with the battery, the traditional source of EMF, gone, then the current in the loop has no choice but to ramp down to zero. And so if that were the case, then across I'm just going to draw the inductor part of the circuit, like that, with the current I coming downward, but now I is a decreasing function of time in that case. Then the induced EMF across the inductor, it opposes that change. It doesn't want the current to go down. So which way will the induced EMF point? What will be its polarity in this case? Well, the induced EMF, curly E sub L, will be that way. Okay? High, potential, and low. The opposite of what we just had, because it doesn't want the current to increase. So we will have to keep track of whether the current through the inductor is increasing function of time or decreasing function of time, because that will determine the polarity of the induced EMF across the inductor. But the bottom line is the induced EMF across the inductor will always have a polarity such as to try to cancel out the change in the current going through it. All right, so let's do a full-blown loop rule analysis of a single loop RL circuit, where we have just thrown that switch S up to point A. And just before that, the current in the loop was 0. And we have just thrown the switch up to point A. So this is now our single loop with a current that's clockwise around the loop and an increasing function of time. And so through the inductor, the current is going downward and increasing. So the induced EMF polarity opposes that. See the little arrow. And now we just apply the loop rule. Conservation of energy. I'll start at this point right here and traverse the loop as a circuit inspector going with the flow, with the current, clockwise. So the first thing is I go through the traditional battery from low potential to high, so I have gain of curly E. Then I go through the resistor with the flow, with the current, so that'll be a potential drop, minus I times R. Then I have a potential drop going against the EL arrow, so minus L di dt. Di dt I know is positive because the current is increasing. So minus L di dt is negative. It's a potential drop. And then I get back to where I started, the total must be 0. And what I want to do is I want to solve this for the current I as a function of time. It's called a differential equation. There's the dependent variable I, the independent variable T, and 3 constants: the EMF of the battery, the resistance of the resistor, and the inductance of the inductor. I will tell you for now just what that solution is when you solve that differential equation for the current. And then for those who wish to see the work, I will show you the math of how you solve that differential equation. But here is what you get for the current as a function of time, for in the case when the current is increasing. You get the EMF of the battery over R out front times 1 minus a decaying exponential function of time, e to the minus t, over a constant tau sub L. That is called the inductive time constant for the circuit, for the loop. Okay? Notice the symbol, tau sub L. That is merely equal to the inductance over the resistance in the loop. Okay? And that means, by the way, that L over R must have the SI unit of seconds, because it must have dimensions of time. And I'm going to show you a plot here in a minute where E over R is 5 milliamps and tau sub L is 2 milliseconds. But first I want to show you how you get that solution for I of t from that differential equation. This is just for those who wish to see and are curious about the math. If you don't, you are welcome to fast forward through this part. I'm going to show you how to solve that differential equation. Let me remind you, it looks like this up here. E minus IR minus L di dt equals 0. And let me rearrange it and write it like this. L times di dt equals curly E minus IR. Let me factor an R out front. Then I have curly E over R minus I. And now I separate the variables, as it were. I multiply both sides by dt, and I divide both sides by E over R minus I. When I do that, And I divide both sides, by the way, by L. Here's what you get. On the left, di over E over R minus I. And on the right, R over L times dt. And then I integrate both sides because I have separated the I and the t variables. The integral on the left is time. Starts at time 0, goes to arbitrary time t. The integral on the right. The integral on the right. The integral on the left is for current, so the limits must be current values. And the lower limit must be the value of the current when the time is 0. Well, in this application, that is 0. I had no current before I threw the switch to point A. And then the upper limit is just the current I at time t. I'll just write it I, but I could write it I of t. Okay, the integral on the right is easy. It's R over L times t. The integral on the left is not too hard either. Just do a u substitution. Let u equal E over R minus I, and then it's an integral of the form du over u, which is natural logarithm of u. And then when you substitute back that u equals E over R minus I, what you end up getting is this on the left. A negative sign, natural log of E over R minus I. And then I just have to put in the limits. Okay? And now let's put in the limits on the left. That's, let me factor a negative out front. Natural log of E over R minus I minus natural log of E over R. Like that. Let me take that negative sign on the left and put it on the right. Then we lose property of logarithms, that log A minus log B is log of A over B. And write this as log of E over R minus I all over E over R. Like that. Then I want to solve for I, so let me take the anti-log of each side, the exponential. That. All right, and then I'm not going to do this last step. It's just algebra. Solve for I and simplify. And you get I equals E over R 1 minus E to the minus R over L times T. And then all the books take that combination L over R and call it the inductive time constant. Okay? So what does that look like when you plot it, right? If you plot the current in that loop versus time, and that's the expression, what does that look like when you do plot it? It looks like this. This is assuming that the ratio E over R is equal to 5 milliamps, that the ratio L over R, which is the inductive time constant, is equal to 2 milliseconds. So I've plotted the current I in milliamps versus the time t in milliseconds. At time 0, the current is 0. You can see that from this formula right up here. When I plug in t equals 0, e to the 0 is 1, 1 minus 1 is 0. The current value starts out at 0. And here we've written that. At time 0, the current in the loop is equal to 0. That means you can think of the inductor at that moment acting like an open switch. It's not letting there be any current for just one instant. Then as time goes on, the current around that loop just ramps up along this curve. 1 minus e to the minus t over tau sub L. So that as time approaches infinity, this expression, the exponential becomes e to the minus infinity, which is 0. 1 minus 0 is 1. So the final current is just E over R. So it just ramps up, the current does, to its final value of E over R, and that means there's no longer any potential drop across the inductor. The whole potential drop you can get in the loop is E over R, and it's across the resistor. So as time goes to infinity, the potential drop across the inductor goes to 0. That means the inductor really isn't doing anything in the circuit anymore. The inductor acts just like a plain old wire. Okay? And so the current just ramps up from an initial value of 0 to a final value of E over R. And the little green triangles that you see down below are in increments of 2 milliseconds. Each increment is one inductive time constant, right? Tau sub L is 2 milliseconds. So after one time constant, the current has ramped up to something like 66% of its final value. After 2 time constants, the current's ramped up even closer to its final value. After 3 time constants, it's closer. After 4, certainly after 5 time constants, you can probably say accurately that the current has reached its final value. So that's what an inductor does in a circuit, at least in the branch of a circuit where the inductor is. It doesn't let the current in that branch change instantaneously. No sudden changes in current. It makes any current changes that happen occur gradually. And the larger the inductance in the branch of the circuit, the more gradual that change is going to happen. Let me show you a Wiley Plus animation of an RL circuit. Battery with EMF E, resistor with resistance R, inductor with inductance L, and an ammeter that measures the current going around. And I can set the resistance in ohms and the inductance in henries. You can see them there on the sliders. And all I have to do is run the animation. That will close the switch at time 0. The current will then initially be 0, and it will ramp up to its final value. And we'll see that on the plot. So let me run the animation. Okay, so the current ramps up. Notice the time constant is L over R. 5 henries divided by 1 ohm is 5 seconds. So the time constant is 5 seconds. And after 5 seconds, we should be at about 66% of the final current. The final current appears to be 12 ohms. And after 5 seconds, we're at about 66% of that. Notice the final current of 12 amps must be equal to E over R. And R is 1 ohm. So the EMF of the battery must be 12 volts in this case. All right, now I'm going to reset, and I'm going to increase the inductance from 5 henries to 10 henries. When I run it, I want you to predict first, how is the graph going to be affected? Think about that a moment. Now, ready? If you made a prediction? All right, I'll run it. Still ramps up to the same final current, but it takes now more time. Because I made L bigger, so I made the inductive time constant bigger. L over R is now 10 seconds. So it takes 10 seconds before we get to about 66% of our final current. So the more inductance the inductor has, the slower the current can change. Okay? All right. Now, the only thing I have left is a little class engagement exercise for you on Blackboard. A little bit more of a complicated circuit, more than one loop, but we do have to be able to deal with multi-loop circuits. It has, in this circuit, 2 identical resistors and an ideal inductor, which means it has only inductance. So the inductor has some inductance L, And this resistor has resistance R, and this resistor has resistance R. I'm going to label this resistor in the middle C for central, or whatever, however you want to think about it. And I'm going to label that resistor A. All right. Here's the question. Is the current through the central resistor, this one, more than, less than, or the same as that through the other resistor, that one? A, just after closing switch S. Right? So just after you close switch S, is the current in the central resistor more than, less than, or the same as the current through the resistor A? All right, same question, but now a long time after the switch has been closed. And now, same question, but just after switch S is reopened a long time later. And then finally, after switch S has been opened a long time. So in those 4 different times, just when I closed the switch, a long time after that, then just as I reopened the switch, a long time after I closed it, and a long time after that. Compare the current in the central resistor to the current in the upper resistor. And that's the series of questions to answer. And then in class, we will talk about RL circuits. And that's all for this video.